Similar problem that we had to what we had in class. So I know a lot of you were probably confused about this. Because, I mean, I know I was. So, but we're gonna make it make sense. I promise. So there's 4 different fields and directions that we want to find, and those are E Coulomb, just the normal B. So this is like our normal E force, our normal B force, and then our E rad and our B rad. So we have 4 different forces that will act on, if we accelerate a charge in a certain direction, at a certain distance away, another charge will experience these 4 different forces in certain directions. And what we want to know, first of all, is what direction are each of these going. So that's the first part of this example today. So for this example, the force that's acting on this charge is positive 5 newtons, so 5 newtons in the plus z direction. So I drew a 3-coordinate thing just so hopefully it'll make a little more sense. Where this z is going kind of negative, it should be a negative z. So, and then our charge is a negative 0.2 Coulomb charge. So because it's negative, it's going to be basically slightly different than a positive if we had a positive charge. So if we accelerate a negative charge in the plus z direction, what we're going to end up with is essentially a current going in the opposite direction. So we can say this: we have a current going in the negative z direction, because moving electrons in one direction is basically the same thing as moving positive charges in the opposite direction, which is what current is. So if you accelerate a positive charge, you just have a current in that direction. If you accelerate negative charge, you'll have a current in the opposite direction. So in this case, we have a current in the negative z direction. And this charge here is at the origin, just so you know. I'm just having these as kind of force vectors. But here's our Q. It's at the origin. So it's being accelerated in the positive z direction around the origin. And so the first thing we want to find is this E Coulomb force. And these are all just directions. So the E Coulomb field is pretty simple. It's just like we did at the very beginning of class, where positive forces will repel, and then negative forces, or negative and positive forces, will attract. So opposites attract, all that stuff. And this P here, this point at 400 meters, exactly in the y direction, is a positive charge, which is kind of what we always assume. If we have a point or a point charge, it's always going to be a positive charge. So if we have a negative charge here and a positive charge here, what direction is the force on this charge P? I heard it. Somebody say it louder. Down. Yes. Okay, negative y. Negative y direction, or down. They will be attracted to each other. So this P should be should have a force on it in the negative y direction. Does everybody understand that? That's just
because Q is negative.
Yeah, it's because Q is negative. If Q is positive, it'd be the opposite. It'd be a positive y. But this is because Q is negative. Okay, so now we have a B field. So our magnetic field has to do with this current. So we just created a current by accelerating our negative charge. So notice how I denoted what direction our current is. So now we can just use right-hand rule, the current right-hand rule, to find our magnetic field using this current. So if you just like we did before, our current is into the page, negative z, into the page. And at y equals 400, x equals 0, and while you curve your hand, just think of it as a normal 2D structure at this point. If you curve it around at the very top, what direction is the force? Yeah, to the right, positive x direction. Right. Does everybody?
Yeah,
Yeah. Okay. So yeah, I drew the z to try and make it so I can show arrows for the radiation. So kind of just bear with me on that. So we should have a negative z current going into the page. So think of it as into the page. And then our point P up here is up here at the top. We should end up having, once again, kind of, if we have this here going into the page, which I guess I should denote as this, then its magnetic field will be clockwise, like this. All that good stuff, you know? Right? So yeah, so into the page, at exactly Y at the top, your force will be in the positive X direction. On the right side, it'd be down, negative Y, all that good stuff. So that's how you find the direction of the magnetic field. So now we have the radiation fields, which are a little more complicated, and hopefully I can make them make more sense. So the ERAD, the radiation due to the electric field, is always going to be in the same direction as the current. So if you find this current, wherever it is, it's going to be in the same direction. So our current is in the negative I, so what you'll end up with is basically these negative Z kind of currents in this radiating field all the way up to P. You end up with, once again, a negative Z irradiation field. It's always in the same direction as the current that we've created. So that's in the negative Z direction, which I can't really say. I guess. Okay. I don't think you explained that very well today.
So it's just
always in the same direction. Yeah, that's how you do it. And then at the point P, the last thing is B radiation field. And since we have, basically this is just denoting basically a wave is propagating in this direction. So you can think of it as like you have a wave propagating in this direction. Okay? And with that direction of propagation, it has a electric and magnetic field that will be going in opposite directions. And so the direction of this wave from this point Q to this point Y is in the positive direction. And so remember, we have to use the other right hand rule to find B. So remember, your thumb is the direction of movement, so the velocity vector. Your hand, or your fingers, should be the E. So in this case, it'll be in the negative Z direction. We found that, as ERAD is in the negative Z direction. So all you have to do is now just curl your fingers, normally, like you would normally curl your fingers, and that gives you the direction of the magnetic radiation field, which is, what direction? Yeah, to the left, negative X. Negative X. Oh, what am I doing? Who wants to go over that again? One more time. Okay, yeah.
Can we use the gun thing that we use?
Probably, as long as you can remember which one's which.
Okay.
So, do you remember which one's which?
Yeah, but it's like a 3.
Yeah, so yeah, you have to remember exactly which one's which. That's the only thing. So, yeah, we will always have the direction, because the direction of wave propagation is always from the point of the charge to this other point that we're interested in. It's just the direction it has to travel between the two. So in this case, positive Y, or in the cases of the examples today, in the positive X. So in this question, it's positive Y, and then fingers just go in the direction of the electric field, which in this case is into the page. Whichever direction your fingers curl is the direction of the magnetic field. So in this case, it's the left. So let's see. So let's say for some reason we had an electric, the ERAD field that was going to the left. Our ERAD was to the left. Our velocity is still up, but if the ERAD was to the left, your fingers would then curl out of the page. So basically, the BRAD is always dependent on what direction the wave's going and the direction of the radiation field, and it'll be in the third coordinate. So if the direction's in the y direction, or the velocity's in the y direction, and the erad is in, let's say, the z direction, then the only other option is x. You just have to determine if it's positive or negative. Okay, we'll do another example, I promise. So that's 4 of the 6 problems that we have to do. So now we get to the actual math, which I'm pretty sure everyone can do. So what is the radiated electric energy intercepted? So now we want to find energy intercepted by a round 1 meter diameter piece of something. I'm not sure. 1 meter object. Yeah, 1 meter diameter object. Well, he says black piece of paper, so we'll do that. Over a time of 20 seconds. So 20 seconds. And remember that the equation is energy is over area times time plus or equals, what was the thing again? Erad
Squared.
Yeah, absolute value of erad squared, which doesn't really matter since squaring it makes it positive either way, over 240 pi. So we have to find erad, which hopefully you guys already have the equation for, and just find the area of the circle, the time, and then plug everything in. So let's all do that together. So
I think you should write the.
yeah. So erad equals.
It's like KQ over R
Is it?
squared. I think, I don't know.
Oh,
If
no,
you have
it's
the piece of
KQ.
paper.
Isn't it KQ? Oh, KQ over R times acceleration
I gave you the piece of paper.
times acceleration over c squared. Okay, so and then we should. I think he wants to
Was
do.
it R squared or R?
It's R squared. It's just R. Yeah, it's just
Okay.
R. Yeah, R squared's only with just the equivalent
Oh,
force.
okay.
So everyone wants to do that. And what's the value of C? Everybody. Good. 3 times 10 to the 8. And then the value of K. 9 times 10 to the 9. Perfect. So everybody can find that. And then acceleration in this case is just 5 divided by the mass. So, and I messed this up today with Connor on accident. Yeah, you have to go to kilograms, not grams. So in this case you have 6 nanograms, which is 10 to the negative 9 grams, and then kilograms is 10 to the negative, or 10 to the third grams. So that's actually like 6 to the negative 12 kilograms, just so you know. So 5 divided by 6 to the negative 12. That's a huge number. Divided by
Stephanie, they're great.
times
She's not coming tonight.
times 0.2 divided by, and then R, remember R is, in this case, is the distance between the two, so 400. So people get like certain values for erad, just erad so far.
Would you want us to leave it in K or?
I multiplied by K.
Oh,
So I got that to you. I got 41.7 ish. Anybody else get that or something?
You said 41.7?
Yeah, I got 41.666. But 9 e to the 9th times 0.2 times what ended up being something gigantic,
Yeah, this is good kilograms.
and then divided by 3 e to the 8th squared and times 400. So yeah, I think I did it.
6 times 10 to the negative 12 kilograms.
Yes. So we got 41.66. Okay, so we're gonna go with that.
Positive and negative, or does that just have to do with the direction?
That just has to do with direction, yeah. So now that we have erad, we can plug that in, and then we can find the area of the circle by just doing, once again, pi r squared, with r being 0.5. So let's work this out over here. So energy is going to equal the erad. So erad was 41.7 squared divided by 240 pi times the area, which in this case was pi times 0.5 squared times t, which was 20 seconds.
It's 240 pi. 240 pi. Is that just?
It's just there. I don't know why. Go ahead and let me know when you guys have. Anybody have a value?
0.868.
What?
0.868.
868. I did not get that. I don't know. Yeah, of course he didn't work it out. Thanks. Nice. Any figures?
The area of the would be 0.25 pi. Is pi r squared.
Yeah. Sorry, I feel like everybody did it. Who got what answers? I don't know what you got. I got 36.2 ish. Okay, so we're gonna go with that one. So 36.2, and energies in joules. So 36.2 joules is the answer to this wonderfully long math problem.